Hello, it's time to do a video. This one's going to be pretty complicated, so strap in. But I wanted to walk you guys through some non-trivial 3D algorithm stuff. It's going to be a little rough, but stick with me, and I'm going to provide the code at the end so you guys can learn from it. All right, let's get started. Stop. If you haven't watched my other videos about basic 3D math, including vector geometry or any of my C++ stuff, and you don't have a good background in it, it might be a good idea to give those videos a watch before trying to watch this one. Otherwise, you might find yourself just a little bit, how do I say this, struggling to follow along. Because I know I would if I hadn't brushed up on this stuff first. Enjoy the video. Allow yourselves to consider a situation where you're making your first 3D game and you have a little guy that you can move around with the analog stick, and it looks really cool. And then you come to the first part because you're an engine programmer and this hasn't already been done for you, that you don't know how to prevent your guy from walking through walls in 3D. Well, that's a problem because you kind of need to do that, otherwise your game's going to suck. And this is one of the probably hardest beginner problems once you start getting into 3D game programming, because the math involved in doing 3D collision detection is not straightforward. And it even took me a little bit of brushing up to prepare this video for it. But I'm going to do my very best to walk you guys through the breakdown of the algorithm in question, the 3D collision detection, its component parts, explain those the best I can, and then we are going to implement it here on this video. And it's going to be awesome. So the first way we tackle this problem is we essentially break it up into its component parts. So instead of thinking about how to handle collision against the entire scene, we break the scene up into its component polygons and think about if we collide with any of these polygons, then we have a collision and we need to handle it. It's very common for game engines to have a completely separate geometry or polygonal scene for collision called the collision mesh compared to what they actually use to render. And this is typically because you want your collision geometry to be simpler than your rendering geometry because it's easier to compute over. So if we were to split this up and look at just one polygon, as I've shown here, in this particular example, I'm only interested in colliding with or testing for collision against polygons that are mostly vertical. In other words, I don't want to worry about the ground in this example. I only want to think about things I consider to be walls. So the easiest way for me to do that would be to consider the normal vector, or the perpendicular to the polygon plane, and to make sure that that normal vector is mostly pointing not up or to some lateral direction. In other words, the y component of that normal vector needs to be mostly 0. Another thing that's important is typically collision meshes are triangulated. They're not always quads. So I'm going to be looking at the actual triangles for my when I'm doing my collision detection and not the planes. It's mostly the same idea, but there's just some slight differences in the way the actual code's going to look. So we're going to start looking at this problem from its 2D side view. We need to come up with a primitive that's a little bit simpler than an entire 3D man walking around to determine what we're going to use for our collision bounding region. The simplest one I can come up with for an example for a quick YouTube video is a sphere. Spheres are really easy to reason about because they're entirely symmetric all the way around. They're uniform. They're just really easy to do 3D math on, and you're going to thank me later. So here's our sphere, what's going to be our bounding sphere that encapsulates our guy. And here's a 2D view of all the geometry in the scene that we are interested in colliding against. Basically, as the guy moves around, we want to make sure that he never goes inside any of these boxes. And if he does, we need to be able to detect that and then push him out of any of the intersections that we encounter. In this particular case, I've shown the intersection polygon in 2D at a 2D side view in white there. So you see right here, this is the 2D side view of the vertical polygon that we've collided with. All right. So there's 3 cases that we need to consider when we need to figure out how the hell do we detect that we've collided, absolutely and surely with one of these polygons. The first case is breaking the plane of the polygon. So every single triangle in 3D space, if you were to take the edges of the triangle and expand them out to forever, will span an infinite plane in 3D space. And that plane essentially can either be broken or not broken by the sphere in question. So here's us extending the plane out into infinite space. And we are interested to know the distance between the sphere and that plane. Without respect to wherever the sphere is, we just want to know how far away it is from the plane. And if that distance happens to ever be less than 0, then we know we've broken the plane. Now, instead of worrying about the distance between the edge of the sphere and the plane, why don't we just worry about the distance between the center of the sphere and the plane? And the idea is that if the distance between the center of the sphere and the plane is less than the radius of the sphere, then we've solved that problem and we know the sphere is breaking the plane of the polygon, and we can detect that, and everything will be fine. However, this is really important to consider that if we happen to be above or outside of the actual real region of that polygon, we can still be considered that we're breaking the plane even though we're not colliding with the polygon. So this is where we start to get into the interesting kind of nuances of this algorithm. The second case is intersecting any vertex. So we know that we are colliding with the polygon if any of those vertices lie inside the sphere. In other words, we can take the distance between the center of the sphere and any vertex, and if that distance happens to be less than the radius, then one of the vertices of the polygon is inside the sphere, therefore we know we are intersecting that sphere, or the sphere is intersecting the polygon. The last case is, we know that if we are intersecting any edge of the polygon, just like with any vertex, we know that we are inside, or the sphere is inside the polygon. Now, some of you might be looking at this and saying, this looks exactly like the plane test. Why would you bother doing this twice? And this really comes down to the limitation of showing 2D representations of 3D problems. In other words, the 3D case of this is a little bit different. So I'm going to switch to the 3D view. And in this case 3, we see that we are intersecting the plane of the polygon, but we are not intersecting any edges. However, if I were to move the polygon to intersect the edge, you can see a very clear distinction between the concept of intersecting the plane of the polygon and intersecting one of the edges. So just like with the vertex case, we know that if we are intersecting any edge in 3D, then we are intersecting the polygon in question. So we can actually combine the 3 cases that we've talked about up until now to determine whether or not we are inside a polygon. We now know that we are inside a polygon if we are breaking the plane of the polygon and we are inside any of the vertices or inside any of the edges of that polygon. Another way to look at it is if we invert all the logic here, we know that we are outside a polygon if we are outside the plane of the polygon, or we are outside all the vertices and outside all the edges of that polygon. Given this information, we can now actually write the code to determine the algorithm for whether or not we are colliding with any polygon in the scene, and then react accordingly. Unlike my usual fashion where I take you guys through the entire program, I think it's not going to make that much sense, and it will be damn near overwhelming to walk you through an entire 3D game, even one as simple as this. So what we're going to do is focus strictly on the implementation of the collision detect function, which is a method I've defined on this character, which is a game object within my game. The character essentially's job is to update the position of the 3D model, the walking guide that you see, and the job of collision detect is going to be to do the collision detection function that we have defined just previously in the slides. So, first things first, we need to worry about our sphere and how our sphere is going to function. So, we need to define essentially the sphere origin, which I grabbed from the model position and shift up a little bit because the origin or position of that model is where the guy's legs are hitting the ground, or feet are hitting the ground, and I need it to be the center of his mass. Next, we're going to take the radius of the sphere, which I just happen to know to be 3 units within the game. And this is important. There are certain cases where I want to be efficient. Though, disclaimer, this is not the most efficient way to implement this algorithm. Still, there are cases where I will compare squared quantities to avoid square roots, which means I typically will take the radius of the sphere and I'll just square it in advance. So I have that ready in this variable here. I'm going to also enable the display of our bounding sphere of our guy so we can actually see him walk around. So that way we'll be able to actually tell based off of our bounding sphere whether or not it's actually colliding with the polygons or not. So we have a loop here that's essentially looping through every single scene object in the entire scene, and we are going to use a test to determine whether or not we are actually interested in testing for the polygons inside the scene object to see if we're colliding with those. So I have a tag that I can set on any given object in the scene, and I have it so that any zero tags or any tags that are zero are the ones I'm interested in actually colliding with. In other words, I don't want the user to try to collide with themselves. I don't want them to try to accidentally collide with the bounding sphere and so forth. Another thing I'm going to do is make sure that everything in the scene is painted white, at least initially during our debugging, so that we know that an object has been collided with based off of whether or not we paint it red down below. Next, we need to actually get access to the geometry of the bounding collision objects in our scene. So essentially, we need to be able to access the vertices, the normals, and the triangle indices of every single triangle inside every single object we're testing within. So this is just some boilerplate code to be able to do that, so I can get the vertex arrays, normal arrays, triangle index arrays, and the number of triangles outside that, and then get essentially the pointer to the arrays of the data that are actually the same ones that are used to draw the OpenGL, or in this case, Vulkan 3D models. Next, we're actually going to loop through every single triangle in the scene geometry, and we're going to define that case that I mentioned previously for each and every one, whether or not we are breaking the plane, or I should say outside or not breaking the plane of the polygon, whether or not we are outside all vertices, or whether or not we are outside all edges. So in the test of whether or not we are breaking the plane of the polygon, first I obtain the three vertices that make up the triangular polygon, and then I obtain the normal to the polygon so that I can use that as well. We are only interested in testing vertical polygons. In other words, if the normal vector of the poly has any vertical component whatsoever, that means it's facing too steep. It could either be the ground, or it can be, something that's a little too steep for me to consider collision against. Or treat. In other words, we want to know whether or not we can treat this as a wall. So in this case, I just do a simple test to see if it's mostly flat, and then we continue onward if anything, if we find polygons we don't want to test. And as you guys know from previous C++ knowledge, continue will just literally skip this polygon and continue the for loop onward. The algorithm to actually determine the point-to-plane distance from model center is something that is pretty reasonably simple. You can find it here. That's where I obtained it from. Again, I think I want to go on a disclaimer here and say I am not like a math genius. I don't have low-level math algorithms memorized. Typically, I have to do a little bit of research and then build those together to make this stuff up. So I don't want to come across as somebody that knows all this stuff by heart, but I know how to leverage it and build it to make things like this happen. So shown here, there's a simple formula that we use to get the point-plane distance from a polygon, given you have this really annoying formatted plane equation. People that have seen 3D math before will typically find that always comes up whenever you're doing any planar polygon algorithms. There's always that A, B, C, D formula for the equation of a plane. I do happen to know from experience that A, B, and C in this equation are always just the normal vector, and D, essentially, I believe, is the distance from the origin to any point on the plane. So I see this equation right here, and I know that I can essentially use it. However, what's annoying to me, or here it is, what's annoying to me about this equation is that I need to get D, and no one ever tells you how to get D, so I just went ahead and looked up how do you get D. And it turns out that if you have 3 points on a plane, or I should say 3 points of a triangle, you can obtain D by computing negative p dot n, where n is the normal vector that we already know, and p is said here to be the average of all the vertices. So this is where I get D. D equals, here's p, that's the average of all three. Negate it, which I forgot to do when I was researching this video, which is really fun, and then dot pn, and that's D. And then I can implement this thing. I recognize this as a dot product, so I do pn dot the origin of the sphere. He mentions here that x0, y0, and c0 are the origin of the sphere, in other words, the center of the sphere that I'm interested in testing for distance from. And then at the end here, he adds D, And then he says you can omit the square root if d is already normalized. And you know what? It is. So we don't need to do that. Finally, I get the point plane distance. I want to determine if it is greater than the collision sphere radius. And if it is, we know that we are outside the plane. If you were to actually look at the logic case here, if we're outside the plane, we don't have to continue into this function and waste computation resources at all. Because if we are not breaking any plane, or if we are not breaking this polygon's plane, then we know we're not colliding with it. So essentially we skip this polygon in that case. So that's the first case. Now we know whether or not we are outside the plane. Let's move on to the second case, which is actually easier of the three, to determine whether or not we are inside any of the vertices, or if any of the vertices are inside the bounding sphere. So that one's actually not too bad. So we know for the given three tests of the three vertices of the triangle, if the distance between the vertex and the origin of the sphere is greater than the radius of the sphere, then that vertex lies outside of the sphere. And in the case where I mentioned above, I want to be efficient, I will square both sides of the equation to avoid a square root, meaning if the squared length of the difference is greater than the radius squared, then we know we are outside. Now, if we are outside all three of the vertices, we now know the answer to the question if we are outside all vertices. So now that part of the algorithm has been essentially done for us. The third part of the algorithm, in other words, determining whether or not we intersect any of the edges of the polygons, is actually one of the more complicated parts. And this is the part that I actually had to look up to figure out because I haven't done this in a while since I've done any kind of ray casting. So, first we know we need three rays from the line segments. So we essentially build three vectors that go around the ring of the actual triangular polygon. And we call those A, B, and C. And those vectors essentially allow us to know the vector from the first vertex to the second to the third, and the third back to the first. And that builds our loop. We declare a variable called intersection point, which we don't use, and then we call this mysterious function that seems to do all the work for us called intersect ray segment sphere, which answers the question, given a vertex and a ray that emanates from it, and our sphere origin, and our squared radius, does this ray intersect the sphere, does this ray segment or edge intersect the sphere? And if all three of these don't, then we know we are outside all edges. Now, I'd do you guys a disservice if I didn't at least go in here, and I'm going to. This is the algorithm that actually calculates this. And I don't steal things without giving credit. So this is the algorithm as it was posted. And this was originally written for people that do things like ray tracing, meaning this algorithm originally assumed that the ray vector was normalized, and I did not want to do that because I am less interested of whether or not we intersect the ray, and I am more interested of whether or not we intersect the ray within some distance that we know is the length of the line segment. So before this algorithm even runs, I take the length of the ray and I divide by it to normalize it so the algorithm functions as it did before, and then when it is finished, I make sure that the intersection distance is not greater than the length. In other words, if we are hitting the ray past the length of the ray, or past the length of the line segment, then it is not a real collision. As far as the actual implementation of this is concerned, I'll leave this as an exercise to the watcher if you want to actually look inside here. It seems relatively straightforward. I believe it has to do with determining the angle of whether or not the ray could ever possibly intersect the sphere. In other words, if the ray is pointing away from the sphere so much that the radius is missed, then you're not hitting the sphere. Going back to our actual loop inside every single polygon, we now can answer the question of whether or not we are intersecting the polygon at all. We earlier bailed out if we were not intersecting the plane, which leaves the final question of whether or not we are outside all vertices and outside all edges. If that's the case, we skip the polygon and we know that we are not colliding with it. However, after this line, we can be certain that we are colliding with the polygon in question, in which case we are colliding with the actual object or scene object that we are iterating through. And we can make note of that by coloring the polygon, or I should say the entire object in red. I'm going to go ahead and run this and see if this works. As you can see, if our sphere in any given point breaks the plane of the polygon or a vertex or an edge, color the entire object red. And I can walk around this entire scene and determine that the collision detection, which is the hardest part of this entire video, is working properly. Yay, because it would suck if it didn't work. Now, as you can see, we've really only done the collision detection test. We don't actually have any code yet to prevent the guy from actually walking into these objects and pushing them out. So we're going to do that next. This part actually isn't too bad. Once I've determined that the character is colliding with a piece of scene geometry, I need to determine which direction to push them to make sure that they remain essentially outside or within bounds of the scene. It's very common for people to solve that problem by using only closed meshes, or meshes that have clearly defined regions of inside and outside, to prevent situations of knowing exactly which direction to push them. In other words, you can see here that the character is defined by a sphere, and we know which side is inside the box and which side is outside the box based off of the 4 directions. If I were to only use thin polygons for my scene geometry, it would be very difficult to know which direction to push the character if they were to actually intersect the polygon. By returning to the box, it's very clear, based off of the normal vectors of the geometry, which way is to push the user out versus which way to accidentally push them back inside. So relying on the normal vectors of the scene geometry and relying on the fact that the scene geometry is closed helps me essentially, reason about this whole scenario. When it comes to situations where you might be colliding with the geometry in multiple places, I simply average the normal vectors of all the collisions so that I can determine which way to smoothly push the character in that case as well. Essentially, when we know that we're already colliding with an object, we make note of a shift delta. In other words, a vector that will push, guaranteed, the user away from the object we're colliding with. Like I showed before, we base that off of the normal to the polygon that we collided with. And as far as the magnitude, we base that off of the radius of the sphere minus the plane distance of from the sphere to the intersected polygon. And then we make note that this collision has occurred, and we add to the number of collisions in the loop. We find at the end of the loop, if we have any collisions at all, we average the shift deltas by the number of collisions, as I showed you in that slide with the averaging step if we hit more than one thing. And this is important just to prevent any ugly jittering and camera sudden changes in position of the user. If we find that the delta length is greater than the walk speed of the character, we essentially make sure that we don't exceed that speed limit, and that prevents us from having ugly shifts. I'm going to run this again. And as you can see, when I try to walk through the scene geometry, I'm pushed out. Let's go ahead and restore the colors of the actual original scene geometry and turn off some of the debugging stuff. And now with all the debugging stuff removed, everything seems to magically work. It's very obvious that I'm using a sphere to bound the character as opposed to something more tight like a capsule, but I'm still really proud of the algorithm. And while it's not perfect, it's pretty decent for an afternoon's work. And I'm really happy to be able to show you guys actually how this stuff works mathematically. Granted, I might not be the world's best person in explaining all the concepts. I hope you guys got a kick out of this video. I'm not going to be able to share my entire engine with you, but I definitely will be able to share with you the code snippets that were actually used to implement this algorithm. Thanks for watching so much, and I hope to make another video soon.